So let me share my screen. Okay, so it looks like someone else wants to join. Okay. Thanks everyone for coming. Today I'm going to be presenting this paper called ZeRO, Memory Optimization Towards Training Trillion Parameter Models. Before getting into the paper, I wanted to kind of give like a high level overview of the problem itself and some key concepts that I think are key to thinking about this paper. So one concept that's I think a primary concept in this paper is the idea that, well, so let's start from really practical. What they're trying to do is they've noticed, and this is something that the deep learning community has noticed in general, that larger models tend to perform better on the tasks that we're applying them to, as long as you have enough data to train them. And we have a couple of fairly known tasks that have huge data sets. The most obvious and most recent one is language modeling and ChatGPT. I'm actually going to do a presentation in a little bit more than a month about ChatGPT, because it's not only, there's a lot of really interesting things they did to develop that, but one of the key concepts is larger models, and because we have so much data to train on it. So we want to make our models larger, but there's a lot of things that are stopping that from happening. One concept that's, I think, important towards understanding why this is hard is the idea that if you take a model and you fix the length of time that you're going to train it for, and you have a fixed size data set, which is always the case, maybe you say, I'm going to train it for 100 epochs, or maybe, like in the case of language models, they actually just give a total number of tokens seen, like 300 billion tokens or something like that. So they don't even go by epochs there. Then there's a large but fixed amount of compute that needs to occur in order to for you to finish training. So when you're measuring compute in these papers, they tend to measure it in flops, which is floating point operations. And for example, in this paper, one number they say quite a few times is that they're able to maintain a performance of 15 petaflops with their training method or their memory optimization, which means that they're able to do 10 to the 15 floating point operations per second. And the reason why that's important is because it means that the higher that number is, the faster the model will train. And when you get into the regime of really large models, okay, so that first important concept, that training a model has a fixed amount of compute, it's measured in flops, and we want the rate at which compute occurs is measured in flops, and we want that to be as high as possible. So what determines the amount of compute that's required, besides the size of the data set and the size of the, actually, well, ignoring the size of the data set, another way of thinking about it is in terms of batches. So the larger a batch is, the larger the amount of floating point operations you need to perform per second. And the larger the model is, also the larger number of floating point operations you need to perform to perform an iteration. So these two things, what they do is they increase the compute required per iteration, and especially in terms of models, because you can, like I said, you can view your data set as a fixed size. Especially in terms of models, you can as your model gets larger, you're going to need to just, for a fixed size data set, you're going to need to perform more computation. It's going to take longer. So yeah, those are two things that affect, and then yeah, those are two things that affect how much computation is required to train a model. But so that's one component of training models, which is amount of computation. The other is memory usage at any given point, and especially like peak memory usage. And so this paper is actually talking about how do you optimize memory usage during training in order to train these really large models? Because the the problem is that like even for, well, first of all, we don't have like infinite compute machines. Like if we had a GPU that had, I don't even know, 1 giga, what is after 1 petabyte of memory, and then one in like a CPU with like 1 million cores and also 1 petabyte of memory, a lot of this stuff wouldn't be an issue. We wouldn't be running into this. But like the cost of GPUs scales, I think, doesn't scale linearly with the memory that they have. And in general, like cheaper GPUs have, over here in this paper, they're talking about V100s as like an average GPU to have access to. And those have a memory of 32 gigabytes. So one issue that you have with these really large models, especially if you want to train them with a larger batch size, is that they consume a lot of memory. So even even if we had like the compute available to train these models, we couldn't, because we can't train them. They don't, the models don't, and the training process doesn't fit on a single GPU. So now the whole paradigm that they're working in is like, how do we parallelize training across GPUs in terms of memory usage so that we can enable the training of really large models? And when you get into the regime of parallelizing across GPUs, and also another key concept for this type of work is the idea of nodes. So a node is like, you could think of it as a computer which has a certain number of GPUs and like a certain size CPU, or maybe multiple, certain size CPU. And if you can fit all of your 1,000 GPUs on a single, like they're talking about here, in a single node, great. Because but you usually can't, and so you have to have multiple nodes and multiple GPUs. And one reason why this is an important concept is because within a node, it's a lot easier to communicate, for the hardware to communicate. So like different GPUs to communicate with each other versus between nodes. So this paper is talking about like, how do we spread memory across GPUs within nodes and across nodes in order to fit these like really large models. And as I said before, like a key component of being able to do that when you're spreading it across this type of hardware is the communication speed, or the communication bandwidth between those hardware components and those nodes. So what a lot of this work is focused on is actually minimizing, as well as minimizing memory usage, is minimizing, as they say over here in the introduction, they want a low communication volume between hardware and a high computation granularity. So computation granularity, and the reason why I'm introducing this now is because it comes up, but like computation granularity is the amount of time that's spent performing computations by your hardware divided by the amount of time the time is spent communicating amongst the hardware. So if you were training a model on a single GPU, there would be an infinite granularity because there's no communication between different components of your hardware. But when you're starting to train amongst different GPUs and different nodes, then communication time is a component of your training time. And so they're trying to find ways to use as little memory on each GPU as possible, while also minimizing the amount of communication that's required between GPUs and nodes, because that would increase the training time and maybe make their as they point out, maybe they make their solution for memory optimization kind of redundant. They actually give a couple of examples in the work where methods that would be like great at optimizing memory, but would take so long that it's not worth using these methods. So let's get into the paper. Let's see. Actually, I actually want to start. I'm going to just go through it as I understand the paper. But if there's some questions that aren't obvious, then let's talk about them. So I want to start this this look at the paper with this diagram here, and introduce some concepts that I found really interesting that I didn't know about. So the first concept or first thing I didn't know is that when you're training a deep learning model, the largest consumption of memory is by your optimizer. I always thought it was by your model, but it's actually your optimizer. And a lot of that actually has to do with the fact that the optimizers that we use today, and they're not just stochastic gradient descent. They have additional components like momentum that you save, and this can have a big increase. This can increase the memory a lot. I'll actually, instead of going to this diagram, I'll read through an example of Atom and how much memory it uses, because I think it's useful. Okay. Oh wait, no, it's over here. Okay. So how does Atom use memory? It says, let's take Atom as an example. Mixed precision training of a model with psi parameters using Atom requires using enough memory to hold a floating point copy of the parameters, so the parameters of the model and the gradients, with memory requirements 2 psi and 2 psi respectively, where psi is the number of parameters. In addition to that, for state-of-the-art methods that are trying to reduce memory, they also have to keep a FP32 copy of the parameters, momentum, variance, with memory components 4 psi, 4 psi, and 4 psi. And then they say, let's use K to denote the memory multiplier of the optimizer states. So in this case, it's 12, because you have to keep these in as well. So you have to keep these saved as well. So overall, if psi is the number of parameters of the model, then the optimizer, just the optimizer, has to keep, in the case of Atom, has to keep 16 times that memory in order to optimize the model. So that while the model itself, you only need one of those. So that's why you have these multipliers that make it so much more use so much memory. Okay, so going back, and that's why you see this diagram here. So this diagram here, what it's showing you is memory consumption by these GPUs in this node or this set of nodes, and the green is the memory of the optimizer. Then the salmon, orange, I'll just say orange. The orange is the gradients of the parameters, and then the blue is the parameters themselves. And each of these three things consumes a certain amount of memory. And they suggest two different types of. So okay, I just wanted to introduce the idea of how much memory these different components use. I don't want to go into it more than that yet. So the optimizer uses the most memory. Now there's two ways that for this paper, or at the point of, actually I think in general, that you can optimize memory. There's more than two ways. There's two like fundamental ideas. One of them is data parallelism, and one of them is model parallelism. Both of them are trying to reduce the amount of memory required by each GPU. That doesn't reduce the total memory requirement. In fact, it might increase it, but it's how do you decrease the total amount of memory required per GPU? And so Model parallelism, also called MP, splits the model vertically, partitioning the computation and parameters in each layer across multiple devices, requiring significant communication between each layer. So essentially, if you have a model and it has 10 layers and you have 10 GPUs, you might put one layer on each GPU and just pass the results from one to another. And that's model parallelism, because then the model, and maybe the optimizer states and all of the things related to it are all on one GPU, are each on one GPU, like 1/10 is on each GPU. But the issue with model parallelism is that it has a high communication issue. It takes a lot of communication, so it slows down the training. Where do they introduce data parallelism? Okay, they must introduce it above. Okay, and the other way of optimizing for memory is data parallelism. So instead of splitting your model between GPUs, you take your batch, however big it is, and you split it into, I don't know, 10. You split it by the number of GPUs you have available. Let's just say nodes for now, because I think it's easier. So you split it amongst the number of nodes you have. And so if you had a batch size of 10 and you had 10 nodes, you could have a batch size of 1 per GPU, or per node, sorry. The plus side of that is that you don't have very high, I think it's that you don't have very high communication requirements, but you have to store a version of the model on every single device. So it has high memory requirements. So you can see like the trade-off. Data parallelism means you can process things faster, but you have high memory requirements per GPU. And then for for model parallelism, you get low memory usage, but high communication or like training times. Yeah, one of our participants said, this is very similar to how IPUs work, except they parallelize across IPUs instead of GPUs. That's cool. Maybe IPUs are the way of the future. But okay, so having discussed that, their their method ZeRO, which they're suggesting here, it tries to take the benefits of model parallelism and put it into data parallelism, a method for data parallelism, and that's their ZeRO DP, or ZeRO data parallelism method, and it has 3 stages. So you can choose to do any of these 3 things, or no, actually you have to do it in, I think, in the order that they show. So you can choose to do optimizer state partitioning, which should have the greatest reduction in memory when you're doing data parallelism, and that's when you partition optimizer states between your nodes. And then you can do gradient partitioning, which should also partitions your gradients between nodes. And then finally, you have parameter partitioning, which should partition your parameters between nodes. So all of these 3 different things are just taking like a component that consumes memory that's kind of independent from each other, your optimizer state, your gradient state, and your parameter state, and you partition it. But you do that while doing data parallelism. So you're splitting your batch across these different GPUs as well. And it can really reduce the amount of memory that you use. They say over here that it can reduce memory by 64 times. And the method, the key idea that they do is that they're able to, they say it over here, by partitioning model states instead of replicating them, and it retains the compute/communication efficiency by retaining the computation granularity and communication volume of data parallelism using a dynamic communication schedule during training. They don't really go that in depth about the dynamic communication schedule, or somehow I missed it having read the whole paper. But anyway, so those are the 3 stages of ZeRO DP, data parallelism. Let's see. And then I have some stuff that I highlighted. So in terms of optimizing residual memory. So when they're talking about memory usage in by a training process, there's 2 different types of, there's a lot of 2s in this paper. There's 2 types of memory usage. One is optimizing for model state, which is what we just described. And then the other one is optimizing for the residual state, where the residual state are things like the activations within the model, because those are things that they're not really permanent. They're just they're an element of the forward and backward pass that you are required for updates, but they're not actually part of the model. They're just part of the computation. And so what they also provide a method which they call ZeRO for zero residual, I'm guessing. And what they do is they again have 3 stages for activations. What they do is, what do they do? They say ZeRO optimizes activation memory by identifying and removing activation replication in existing model parallel approaches through activation partitioning. It offloads activations. Okay. So what they do is they like partition the activations again between the different nodes, and they that saves memory because you don't have to have all the activations on all the different GPUs. They do something which is they define an appropriate size for temporary buffers to strike a balance between memory and computation. So supposedly a lot of different like training methods, they have like a dynamic buffer which they use to speed up computation. And dynamic, I mean in terms of size, but that can be a problem because your buffer can explode in size and that can consume a lot of memory. So they fix the size of the buffer based on some algorithm. We'll go over that a little bit more. And then one last thing that they noticed, which I actually think I've hit quite a few times. So I was like, oh, I wonder if I could, even within a single GPU, and I'm wondering if I could just find a way to get rid of this, which is we observe fragmented memory during training due to variations in the lifetime of different tensors. And it says lack of contiguous memory due to fragmentation can cause memory allocation failure, even when enough free memory is available. So that's a lot of terminology. Essentially, contiguous memory is memory that's like, you can think of like memory as maybe this massive set of lockers. And contiguous memory is lockers that are all right next to each other. And you need that to store certain types of things like certain tensors or parameters. Probably just because you don't want to have to like go to one locker and then one that's like a million lockers away. And so for certain things that are stored in contiguous memory, you need to have that amount of contiguous memory free to store them. So you'd need, like, if you had a matrix that's 3 gigabytes in size, you'd need 3 gigabytes of contiguous memory available. But the way that these training processes work is that they're constantly taking up memory, like contiguous memory in different spots. And this can cause fragmentation because there's no optimization there to make sure that there's large amounts of contiguous memory available at all times. Instead, they're just kind of like taking what they can. And so the authors, they realize that they can use some simple observations in order to free up a lot more contiguous memory within a GPU so that you can use the full amount of memory within the GPU. So that's optimizing residual memory states, residual state memory. I didn't, that's not important. Yeah, they say we show that ZeRO can be combined with model parallelism, resulting in a max theoretical memory reduction of the number of so the degree of data parallelism is the number of partitions is this a problem? So someone said, is this a problem with Python or also C++? I think the underlying code for all of this is in C++. Like CUDA isn't written in Python, and it's dealing with memory usage. So I'm guessing that all of this is C++. I don't know though. This is a wild guess on my part.
Sorry, Peter, I didn't mean to stare on him. I was just wondering because Python's garbage collector can cause problems, right? Maybe if you do it, if you write in C++ with optimized garbage collection and whatnot, then you may do it better. Is it what they are doing here?
Well, I don't know what language they're using, but I know it's not Python. So
okay.
I'm guessing probably. So just to go back to the sentence I just read, where it says we show that ZeRO can be combined with model parallelism, resulting in a maximum theoretical memory reduction of ND by N times on each device with a DP degree of ND and an NP degree of NM. So the degree is the number of partitions that you're with respect to data parallelism and model parallelism that you're using. And so what that means is that if you combine ZeRO with DP, so like say you used one or two of them by themselves. So if you use ZeRO by itself and you had 64 partitions, then you would get an increase in a decrease in memory of 64. If you use model parallelism by itself, I'm guessing you would also get a decrease of 64. But if you use them together, then you'd be able to split if you split them half. So you'd have a degree of 32. Oh no, they also have to equal the number of I guess it would be 8 by 8. Anyway, I'm not going to go down that route because I don't think I understand it well enough. Obviously, this isn't my area of expertise. But cool result. You can combine ZeRO with model parallelism and get even better scaling. So like I said before, we're actually still in the introduction, but the point that they make is like, okay, we've suggested all these great ways of reducing memory usage, but they're still able to maintain a high flops rate. So they're still able to have really high computation in terms of how fast they're training models. In terms of scalability, they say we observe super linear speed up in regimes of 64 to 400 GPUs, where performance more than doubles when we double the number of GPUs. So they're saying like we see more than a double in speed of computation. Or is it super linear? I guess performance is in terms of memory usage, and they say this is a property of ZeRO-DP, which reduces the memory footprint of the model states as we increase the data parallelism degree, allowing us to fit larger batch sizes per GPU, resulting in better performance. Cool. So one point that they make is that they are democratizing large model training for data scientists. One, because, well, I think the main reason that they say is because their methodology for like the software that they put out with this, which is called DeepSpeed, it's just like a wrapper around any torch model. That's like a torch.nn.module, which is like the way that you express all torch models. So it's really easy to use. The one thing I don't think that's super clear here is that you don't see a huge speed up or like a huge decrease in memory consumption when you have few GPUs. And I'm not even like I'm pretty sure, but I would love to ask an author, like, if I had 2 GPUs, should I be using DeepSpeed to train a model, or is it just going to slow things down? Like, I guess you always decrease the memory usage, but how much is it going to slow down the computation, like the speed of computation? Okay, so that's the introduction. We got through that, and we're on page 6. Related work. They by the way, through this paper club, I'm just hoping to introduce a lot of concepts. I don't think I'm going to be able to present like a really in-depth analysis of this, but for me, it was like an educational experience to read this paper because of all the concepts I learned about. So there's another form of parallelism called pipeline parallelism, which they don't mention before this. And they say, and they showed in the related work, and they say pipeline parallelism splits a model horizontally across layers, running each partition on different devices and using microbatching to hide the pipeline bubble. Model functionality such as tide weights and batch normalization are difficult to implement due to horizontal splitting and microbatching. I'll be honest, I don't really understand that. To me, horizontally across layers means that you take a layer and you, I don't know, you split it. But how do you split like a matrix? Unless it's a block diagonal matrix or something like that, or it's a block matrix. I guess it doesn't have to be diagonal. So I wasn't sure about that. But there's another form of parallelism called pipeline parallelism. Okay. So they talk about different things. So we're just going through the related work here. To deal with residual state optimization or activations, especially reducing activation memory has been done by compression, activation checkpointing, which means you save it and then load it again later instead of keeping it in memory, and or in live analysis. And they say that what they're doing with ZeRO works in parallel with activation checkpointing. So you could do that too. Another common method for storing the residual state is to actually offload it to CPU. So you send all of your activations in the forward pass to the CPU, so it doesn't have to be kept within memory in the GPU. And then during the backward pass, you load them again, or you send them back to the GPU. And they say that ZeRO differs in that it reduces memory consumption without storing the model states to CPU. But they actually have, like, what's interesting about this is that they do offloading to the CPU in the case that the model is so large that you couldn't train it without doing that. So maybe sometimes you'll have to send your activations to the CPU after the forward pass just to reduce the memory consumption. Yeah, this is important. Okay. So we've talked about it's like where do the next section is called where did all the memory go? This is just what's using all the memory in a GPU. We kind of talked about this before. The largest use of memory is by the optimizer states. One thing I glossed over when I was talking about Atom is that, I'll just read it here. The state-of-the-art approach to train large models on the current generation of NVIDIA GPUs is via mixed precision floating point 16 and 32 training, where parameters and activations are stored on floating point 16, enabling the use of the high throughput tensor core units on these GPUs. And then they also have to store what we talked about before, and as like the parameters and then the optimization states, like the momentum and variance on floating point 32 for updating them. So they use a lot of memory using Atom, or like any other of these optimizers that's got some like first or second order statistics. And then for residual memory, the things that take up memory are like are just activations. We've talked about it a little bit before. Something else that can cause memory usage is buffers used during training, and that's just because they can explode in size unless they're kind of regulated. And memory fragmentation, where there's not a lot of contiguous memory available. So that's stuff related to residual memory consumption. Yeah, let's talk about. So that's just some stuff about what uses memory, activations, parameters, gradients, optimizer states. And then ZeRO insights and overview. I actually don't think I'm going to go into the detailed section just because it's like, there's a lot of repetition here. So here are the insights and overview for ZeRO-DP, so the data parallel section. Data parallelism has better scaling efficiency than model parallelism because model parallelism reduces the granularity of the computation while increasing the communication overhead. Makes sense. And this is true especially when crossing node boundaries. So this is what we talked about before in terms of the trade-off between data parallelism and model parallelism. And then the second, we know that the second insight I'll go over is that both data parallelism and model parallelism keep all the model states needed over the entire training process, but not everything is required at all times. For example, parameters corresponding to each layer is only needed during the forward and backward propagation of the layer. And this kind of gives an idea of what's going on under the hood, by the way. So they partition the optimizer state or the model layers between different GPUs. But then when they're required for doing a forward pass or a backward pass or calculating doing the optimization, they gather them, or they gather them on each of the nodes or that you're parallelizing across, and you're performing the computation, but you're able to request like a much smaller part of the model or the gradients or anything because you're only using the part you need at the time you need it instead of having all of it available. Yeah, that's the big idea. ZeRO-DP partitions the model states instead of replicating them and uses a dynamic, yeah. So actually, I wouldn't want to gloss over this. I hope what I just said is important because it got through, because I think that's like the key idea of why all of this works. They're doing data parallelism, but they're only requesting what they need from like the model, the optimizer states, and the gradients at the time they need it on all of the GPUs. So you don't have to store everything all the time in all the GPUs, and instead they are stored on all of the GPUs, but in partitions that are much smaller, and then only requested by the other GPUs. Like that partition is only requested when it's needed. That's like the key idea for ZeRO-DP. And then for ZeRO-R, let's see. I guess I'll read the second overview. For ZeRO-R, this is for optimizing the memory usage of the residual state. It says, for models such as GPT-2 or larger, the arithmetic intensity, the ratio of the amount of computation per iteration to the amount of activation checkpoints per iteration, is very large, 10K larger, and increases linearly with hidden dimension, making it possible to hide the data movement cost for activation checkpoints, even when the bandwidth is low. So I guess they're saying something along the lines of, with these really large models, the amount of time it takes for computation, or like it means that you can like do the two things in parallel of sending memory across machines while performing the computation, such that like there's very little extra time being consumed. Okay. Yeah, so here's the deep dive. I don't really want to go into the deep dive, but I'll just state some quick quick takeaways from the deep dive that I thought are like more important terminology. There's these ideas in parallel computing called like the all gather method, and there's like reduce scatter. There's all of these. So basically, there's two kinds of methods, I think, or there's more, but like that they mention here, which are when you you take something and you want all of the machines to have access to it. So that's called an all gather. So for example, you want to get the the first 5 layers of the model, you all gather it to all of the different GPUs. That's like a term in parallel computing. And then they also have something called the reduce scatter or reduce gather, which is kind of the opposite. Whenever you're scattering something, you're sending it, you're distributing it amongst GPUs, and reducing is just like reducing the size. Maybe you guys came across this when you're reading it, but if you see it in the future, you'll know that it's some kind of, it's a term for basically distributing memory or between the different nodes. Cool. Like I said, I don't want to go into the deep dive, so I think I'm just going to go into the results. Yeah, I'll go into the results. If you're interested, I would recommend reading the deep dive, but this paper kind of explains everything in the introduction, then explains it in a little bit more detail in the, I see someone has their hand raised. Inika, you have your hand raised.
Mm-hmm. Yeah, something I don't really get and I'm wondering is that they mentioned the caveat of doing model parallelism is that the communication will be difficult. And here when they partition the activations, that they save this activation checkpoint and they will load only the necessary checkpoint for in every node. I'm wondering how do we handle the communication between that, and how do we know that this is the latest checkpoint in the activation? It's like I'm wondering if they have like what a master node or something like that to store the like the latest state or to handle this communication.
Well, I don't think they would probably just override the activations every time they save them. Checkpointing is actually not a part of this. What is it? Let's see. They say that checkpointing can occur in parallel with ZeRO-R. So they don't actually checkpoint in their ZeRO-R method. Yeah, but you could checkpoint, and maybe it's just saved in a specific place. And okay, you could just interrupt me.
Yeah, no, I don't know because I read in some bits they mention about this activation checkpointing. Like they do activation partitioning by saving the checkpointing, but maybe I misunderstood that part. So I'm
They
not
don't
really
do
clear.
they don't do checkpointing. They could do checkpointing. Checkpointing means that you like save it and then load it again. Here they're just partitioning, so they're putting it into different GPUs.
So
But you
what does
could
it mean by partitioning?
partitioning means that it's always loaded into memory instead of being stored. And then you're partitioning it across the different GPUs. So if you had like 10 gigabytes of activations, and then you had 10 GPUs, then you would each GPU would have 1 gigabyte of activations on it.
And then they will need to pull all of this. I'm trying to understand this concept.
What they do is that they pull the activations when they need it. So when you're doing a backward pass through the model, you only need the activations for layer 5 when you're doing your backward pass through layer 5. So they would only pull the activations from the partition that has the activations for layer 5 when they need it for that backward pass.
Okay.
But you could also checkpoint instead, or at the same time, I guess. Yeah, you could also checkpoint, so you don't even have to partition. You just save it somewhere and load it.
Cool.
Yeah. The deep dive, like I said, if you're interested, would recommend, but it's kind of, there's a lot of repetition between the different sections. It's just a little bit more detail each time. I think we can talk about the results through a couple of tables. Here's the table that kind of talks about how the increase in performance. So increase in performance is like what size model you can train on this number of GPUs. So they're assuming all the GPUs have 32 gigabytes of memory. And I think they're assuming a fixed batch size because you kind of have to. Right? I think you have to, but maybe not. But anyway, so with one model parallelism and 64 GPUs using their, without any of the memory optimizations, you could train a $2 billion parameter model. When you're just optimizing for memory states, you can do a model that's 7.6 billion with gradients as well, 14.4 billion, and then with all three, 128 billion. And then, let's see, measured model size. And then what they were able to get, for example, with just the first one is, so you can see they said that the theoretical model size was 7.6 billion, but if you look over here, they were able to make it 6.2. But so with model parallelism of 16 over 1024 GPUs, they were able to train a model with 100 billion parameters. And but they said the maximum theoretical size, if they were to use all of the optimizations, was 2 trillion parameters. So 20 times larger. Yeah, 20 times larger. So that just shows you how they're able to, how large the models are that they're able to train. And in the results section, they do say something that I think was interesting, which is they point out that their method is where is it? Okay, so yeah, this is a compute gap. They point out like the whole, like the paper itself, they're talking about how cool it would be to train a trillion parameter model. But what they say is that a trillion parameter model, even if you optimize memory as much as possible so that, and have a very low computation, the low computation overhead that they have, it would take 3,000 times 67 minutes. And that's just because of how large the model is. So this is like how much time it would take. So it would take about a year to train that model, even with even though we've solved the problem of memory optimization in terms of training models, and we could train a trillion parameter model, it would take like a year to train. And at that point, it might not be useful because you just don't know if you're going to get that performance with the hyperparameters that you chose. So, oh, it says it will take 140 days, so half a year, sorry. So what they did for like deep speed is they actually created a version of ZeRO, which they're calling ZeRO 100 billion, which is optimized for training models that have in the hundreds of billions of parameters. And that's the one that they're evaluating methods on, because they're like, we can't really train trillion parameter models yet because we don't have the compute. Like, essentially, I think what they would need is data centers with a lot more than 1,000 GPUs in order to be able to train the model faster. And it's hard to find that, I guess. Makes sense, but I just don't know what kind of large data centers are out there or how expensive they are or any of that. So they've released this ZeRO 100 billion, and there's a ton of different results. None I think are like, if you're interested, I would encourage you to read about the results. But the only cool thing that I think, or not the only thing, one cool result which is worth mentioning is that they use their method to train like the largest at that time language model ever, which is called like Turing NLG, and it had like state-of-the-art, Turing, it had state-of-the-art accuracy at the time. The model was 17 billion parameters, which at the time was the largest. I think GPT-3 has like 175 billion now, and I think we might have even passed the trillion mark on some other ones. But this paper was published in 2020. So yeah, that's the paper. I'm happy to answer any more detailed questions. I know I didn't go into some of the more detail. I thought it was really cool, and like I said, they released this memory optimization package called Deep Speed with that is this paper. And actually, since Deep Speed, like PyTorch has integrated its own version of this idea it's called like fully sharded data parallel something. If you type in like fully sharded data parallel PyTorch, it will come up. So this paper has been implemented quite a few times by different people and the ideas in it in order to be able to scale models. That's why I chose it, because I was like, oh, these ideas are popping up in a lot of different places when I look into memory scaling issues. Scaling issues with respect to memory. So yeah, if you're trying to train a really large model, I would encourage you to, like, this is a solution you could use, Deep Speed or fully sharded memory from PyTorch. Thanks. Does anyone have any questions? No? Cool. Well, thanks everyone for attending.
Thanks, Peter.
Thank you very much. Very good.
I know it's a bit of a different paper than we usually talk about, but I think it's interesting to have like a diversity of papers. And I hope everyone has a good weekend.
Thank you very much. You too.
Bye-bye.
Jack, I'm not sure what we're going to be presenting next week. It will be ML focused again. So when I say ML, like not software engineering related part of ML. But we usually post it on Mondays, so we'll post it on Monday.
Yeah, thanks a lot. That was very informative.
Great.
Thank you.
Have a good one.